Hi, hi. Welcome to Math 250. I hope that, welcome again to Math 250. So I hope that this time around the audio is better. I hope that this time around the audio is better. Okay, so today what we're going to do is we're going to lecture some more on exponential functions. So today we're going to do two things. The first thing is we're going to look at some exponential word problems, some word problems involving exponential functions. So some exponential word problems. And then we're going to look at, and then after that we're going to look at other miscellaneous problems involving exponentials. So miscellaneous, I hope I spelled this right, exponential problems. Okay, miscellaneous problems involving exponential functions. Okay, so those are the two things we're going to look at. First, we're going to look at exponential word problems, and next, we're going to look at some miscellaneous problems involving exponential functions. First, let me recall what an exponential function is. So previously, we introduced exponential functions, and recall what an exponential function is. Recall what an exponential function or an exponential is. Okay? So an exponential function is just a function that has the form of an exponent. Okay, that's what an exponential function is. It's just a function that has the form of an exponent. So it's a function of this form. Pt equals to p naught times a to the power of 2. Okay, it's a function with the form of an exponent where the input variable is in the power. Okay, is the function with the form of an exponent where the input variable is in the power. Okay, so that's an exponential function. Okay, it's a function of this form. And what is p naught and a? Well, p naught and a are just concrete, strictly positive numbers. So where p naught and a are strictly positive constants. Okay, they're just concrete, specific, strictly positive numbers. Okay, so that's what an exponential function is. It's just a function of this form, a function that has the form of an exponent, okay, where the input variable is in the power. And recall that for exponential functions, there are two cases, right? For exponential functions, there are two cases. So the first case is the case where this base is strictly bigger than 1, and that's the case of exponential growth. Okay, that's the case of exponential growth. Okay, so that's the first case of exponential functions, where this base a is strictly bigger than 1, and that's exponential growth. And remember what the picture for exponential growth is. The picture for exponential growth is roughly like this. And that's roughly the picture for exponential growth. Can you see this? Yeah, so that's roughly this picture for exponential growth. So as you move forward in time, the function blows up to infinity. Okay? As you move forward in time, the function blows up to infinity. That's the picture for exponential growth. And then the other case, is where this base a is now strictly less than 1. Okay, it's always greater than 0. And recall that that's the case called exponential decay. That's the case of exponential decay. And recall what the picture for exponential decay is. The picture for exponential decay is like this. So as we move forward in time, the function decays to 0. Okay, as we move forward in time, the function decays to 0. So those are the two cases for exponential functions, okay, where this base a, this thing over here, is strictly bigger than 1. That's exponential growth. So that's the case where as we move forward in time, the function blows up to infinity. And the case where the base a is strictly less than 1, that's called exponential decay. And in this case, as we move forward in time, the function decays to 0. Okay, those are the two cases. Okay, so now let's look at some exponential word problems. Let's look at some exponential word problems. So we'll look at a word problem. Some word problems. Okay. To explain these exponential word problems, I'm going to divide the board up into two columns, the left-hand column and the right-hand column. Okay, so to explain the exponential word problem, I'm dividing the board up into two columns, the left-hand column and the right-hand column. Now, in the left-hand column, what I will do is I will explain the theory. Okay, I'm going to explain the theory in this left-hand column. And in the right-hand column, I'm going to give you a concrete example which illustrates the theory. Okay, so in the left-hand column, I will explain the theory. And in the right-hand column over here, I will give a concrete example that illustrates the theory. So in the left-hand column, I will give you this proposition, which is basically the theory. Okay, this proposition is the theory. And in the right-hand column, I will give you an example, which illustrates the proposition. Okay, a concrete example which illustrates the theory. Okay, so left-hand column, the general theory or the proposition. Right-hand column, a concrete example which illustrates the theory, the proposition. Okay, so here's the proposition. Here's the theory. So first, suppose that you have this quantity that you're interested in. Okay, you have this quantity that you're interested in, and this quantity changes by a certain percentage per unit time. Okay, it's important that the quantity changes by a certain percentage per unit time. Suppose that we have this quantity that we're interested in, and this quantity changes by a certain percentage per unit time. So say that a quantity P equals to PT, this is the quantity that we're interested in. So say that we're interested in making future predictions about this quantity, and say that this quantity changes by a certain percentage per unit time. So it's important that it changes by a certain percentage per unit time. So increases or decreases. So it changes by a certain percentage per unit time. Okay, so we have this quantity that we're interested in, and it changes by a certain percentage per unit time. Okay, so some quantity that we're interested in making predictions about, and it changes, it increases or decreases by a certain percentage per unit time. Okay, so for the concrete example, say that the PT that we're interested in is, say, population. Say that the PT that we're interested in is the population of a village in year T. So say that PT is the population of a village in year T. Okay, so T years after some year which we say is T equals to 0. Okay, say that we're interested in making future predictions of the population of a village T years after some year which we designate as T equals to 0. So T equals to 0 can be, say, like 1620. T equals to 0 can be, say, 1925, or T equals to 0 can be like 2005 AD. Okay, so say that we're interested in the population of a village T years after some year which we say is T equals to 0, and T equals to 0 can be, say, 1980, for instance. And okay, for this to fulfill this theory, it this quantity has to change by a certain percentage per unit time. This quantity has to change by a certain percentage per unit time. So say that the population of the village is going down. Say that the population decreases by 2% per year. Say that PT decreases by 2% per year. So it's changing by a certain percentage per unit time. It's decreasing by a certain percentage per unit time. It's decreasing by 2% per year. Okay, so say that the population is going down by 2% per year. So it's changing by a certain percentage per unit time. So it satisfies this theoretical requirement. Now, okay, so now back to the theory. Okay, so we know that we have this quantity that we're interested in, and we know how it changes. It changes by a certain percentage per unit time. But now, let's say that we also know what the initial quantity is. Okay, so in other words, let's say that we know what the quantity is at time t equals to 0. Okay, whatever time t equals to 0 is. Say that we know what the initial quantity is at time t equals to 0. So let P naught be the initial quantity, meaning the quantity at time t equals to 0. At time t equals to 0. Okay, so say that we know the initial quantity. Okay, so we have this abstract quantity, this quantity that we're interested in. We know how it changes. It changes by a certain percentage per unit time. And not only that, we also know what it was at the beginning of time. We know what the initial quantity is, what the quantity was at t equals to 0. Okay, now back to the village example, the population of village example. Let's say that in year 0, in year t equals to 0, and as I said, year t equals to 0 can be anything. It can be, say, 2007 AD. Year t equals to 0 can be like 1851 or something like that. So let's say that, okay, so let's say that we knew that the population of the village, let's say that we knew that in year t equals to 0, whatever that year was, the population of the village was, say, 100 people. Okay, let's say that in year t equals to 0, we knew that in year t equals to 0, the village had 100 people in it. So say that the village started with P naught equals to 100 people, 100 persons at year t equals to 0. Okay, so say that we knew that the village started with 100 people in year t equals to 0. Okay. Okay, so okay, now let's go back to the abstract theory, the proposition. We have this quantity PT, which we're interested in. We have this quantity PT that we're interested in. And we know how it changes. It changes by a certain percentage per unit time. It changes by a certain percentage per unit time. And we know what the initial quantity is. We know what the quantity was at time t equals to 0. So if we know the initial quantity, and we know how it changes by a certain percentage per unit time, then the theory says that we can predict what that PT is at all future times t. Okay, so if we have a quantity, we know how it changes by a certain percentage per unit time, and we know the initial quantity. We know what the quantity was at time t equals to 0, then we can predict what that quantity is at all future times t. And the conclusion, the prediction, okay, so this is still the theory. The conclusion, okay, so the conclusion is that at all future times t, the quantity is an exponential function. Okay. Namely, it's an exponential function of this form. P naught, and we know what P naught is. It's the initial quantity. It's the initial quantity which I just erased, times 1 plus r to the power of t. Okay, we know what P naught is. It's the initial quantity that we erased. But what's r? R, remember, we knew that how the quantity changed. It changed by a certain percentage per unit time. It changed by a certain percentage per unit time. What's r? R is the decimal representation of that percentage per unit time. It's the decimal representation of the percentage rate of change, where R is the decimal representation of the percentage rate of change. It's the decimal representation of the percentage rate of change. Okay, so the things that I erased, the hypotheses, was we know what the initial quantity was. The initial quantity at time t equals 0, it's p naught. We knew how it changed. It changed by a certain percentage per unit time. It increased or decreased by a certain percentage per unit time. And what's r? So then, at all future times t, pt is this thing, where p naught is that initial quantity, and r is the decimal representation of that percentage rate of change, right? Remember, the quantity changed at a certain percentage per unit time, and r is the decimal representation of that percentage. Is the decimal representation of that percentage. And note that this is an exponential function. 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 Is the writing clear? Okay, this is an exponential function, and the base of this exponential function, a, is 1 plus r. This is an exponential function where a is 1 plus r. A is 1 plus r. Okay, is everything clear? Right, so this is an exponential function. Exponential function where the base a is this 1 plus r. Okay, now let's apply that to the theory. Okay, so this thing satisfies the hypotheses of the theory. We know that we have this quantity, the population of the village t years after whatever is year t equals to 0. We know that it changes by a certain percentage per unit time. Okay, we know that it changes by a certain percentage per unit time. It decreases by 2% per year. And we know what the initial quantity was. We know what the initial population in year 0 is. It's 100 people. So then it must satisfy this formula. We know how to predict what this population is in all future years t, namely it's this exponential function. It satisfies this formula. So in year t, villages population in year t, the population of the village must satisfy this formula. Is pt equals to p naught. Okay, so it's the initial quantity, the initial population, the population at time t equals 0, which is 100, times 1 plus r. R is the decimal representation of the percentage rate of change. Is the decimal representation of the percentage change per unit time. Well, we know that it changes by 2% per year. So since it's increasing by 2% per year, that means that the decimal representation is 0.02, right? 0.02. So then put that down here. So it's 0.02 to the power of t. So then it's 100 pt is 100 times 1.02 t. And don't forget the units, people. So this many people will be in the village after t years. After t years. So is this clear? Okay, this should be clear. After 2 years. Okay, let me just write this. Let me just write this many people in year t. In year t. Let's just write that. Okay, so is this clear? Okay, so then this is oh no, it's decreasing by 2% per year, so it's minus 2%. So it's r is equal to minus 0.02. So this should be a minus, right? Because it's decreasing. The population of the village is going down, so it's minus 2% per year. Minus 2% per year. So then r is minus 0.02. So this r should be minus 0.02, so then it should be 0.98. Okay, so it should be this many people in year t, this many people in year t. Okay, because it's decreasing. It's going down by 2% per year, right? It's decreasing. So it's minus 2% per year. So then the decimal representation of minus 2% is minus 0.02. So that's what you should put into the R. That's what you should be putting into the R, minus 0.02. So it's this many people in year t. Is it clear? Okay. Okay, so 100 times 0.98 to the power of t people in year t. Okay, and don't forget the units. Okay, for word problems, you should always have units. Okay, so let me just repeat the general theory. Before going on, let me just repeat the general theory. Even though I've erased it, I've erased much of what's on the theory side of the board, on the proposition side of the board. Let me just repeat it. If you have a quantity, if you're a quantity and you're interested in making future predictions about this quantity, and if you know two things, the first thing, you know how it changes, and it's important that it changes by a certain percentage per unit time. It has to change by a certain percentage per unit time. So if the first thing is you know that this quantity changes by a certain percentage per unit time, increases or decreases by a certain percentage per unit time. And second thing, the second thing is that assume also that you know what the initial quantity is. You know what the quantity at time t equals 0 is. Okay, so assume that you have a quantity that's changing and you're interested in making future predictions about that quantity. And you know two things about that quantity. First, you know that it changes by a certain percentage per unit time. So you know how it changes, and it changes by a certain percentage per unit time. That's important. That's important for this theory to work, that it changes by a certain percentage per unit time. And the second thing is you know what the initial quantity is. You know what the quantity at time t equals 0 is. Then you can make future predictions about this quantity. Namely, this quantity is an exponential function. It's an exponential function of this form. Okay, the quantity is an exponential function of this form, where p naught is the initial quantity, and r is the decimal representation of that percentage rate of change. Okay, remember, we assume that that quantity changed by a certain percentage per unit time. R is the decimal representation of that percentage. Okay, so then it's an exponential function where the base is 1 plus r. Okay, the base is 1 plus r. Okay, and this is a concrete example of that. Okay, this thing on the right-hand side is a concrete example of that. Okay, let's look at some other examples. Let's look at some other examples. Let's look at this example. Okay, so let's look at this example. Okay, let's look at this example. A 50 milligram dose of quinine is given to a patient to prevent malaria. A 50 mg dose of this drug, quinine, is given to a patient to prevent malaria. Okay, so a 15 milligram dose of this drug is given to somebody, given to some patient to prevent malaria. This drug, here's an interesting fact, and that is this drug, quinine, leaves the body at a rate of 6% per hour. So here's an interesting fact. Quinine leaves the body at a rate of 6% per hour. Okay, this is an interesting fact. So the first part of the question asks you to find the amount AT in milligrams of quinine left in the body T hours after the dose is given. Find the amount AT in milligrams in mg of quinine that's left in the patient T hours after the dose is given. T hours after the dose is given. Is this clear? Is this clear? It looks like it's clear. Okay, so find the amount in milligrams of the drug that's still inside the patient T hours after the dose is given. B, how much quinine is left in the patient, in the body of the patient, after 24 hours. After 24 hours. And C, roughly sketch the graph of the function dt. Okay, let's see if I wrote this down correctly. Okay, so before going on, let's sketch the scenario. Let's sort of describe the scenario. The scenario is that you have a patient, and to prevent this patient from getting malaria, he or she is given a dose of this drug. Okay, so you have a patient, and to prevent this patient from getting malaria, he or she is given a dose of quinine, this drug, quinine. And okay, so the person gets this dose of the drug. He or she either eats it or gets it in his body in some other way. And after the dose of the drug, the quinine is inside the person. After the 50 milligrams of the drug is inside the person, it starts leaving the person. And it can leave the person in various ways, right? It can leave the person by sweating, or the drug can leave the person by sweating, or the drug can leave the person by like urinating or bowel movements, or so on and so forth. So after the person gets this initial dose of the drug, by eating or some other means, it starts leaving his body by sweating, urinating, so on and so forth. And we have an interesting fact over here. This is probably probably an interesting experimental fact, and that is somehow we know. Okay, so some interesting experimental fact. We know that this drug, this quinine, leaves a person's body at a rate of 6% per hour. Okay, this is an interesting experimental fact, that this drug leaves the person's body at a rate of 6% per hour. Okay, that's an interesting fact. Okay, so that's the scenario. Person gets an initial dose of the drug, and then it starts leaving his or her body in various ways. Okay, now, as always, before I start doing the problem, I always begin by first specifying the variable of interest. I always begin by specifying precisely the variable of interest. And recall that the reason why I do this is oftentimes, okay, sometimes, maybe even a lot of times, specifying the variable interest may be like sort of trivial or redundant or so on and so forth. But I always like to do this first. I always like to first specify precisely the variable of interest, because it makes clear and precise what the problem is inside my head. Okay, by specifying the variable of interest precisely, it makes very clear and precise inside my head what the problem is. Among other things, it makes precise what the units are. It makes precise and clear inside my head what the units are. So first, let's specify the variable of interest. So what's the variable of interest? Okay, what's the variable of interest? Well, clearly, in this problem, the variable of interest is the amount of the drug, the amount of the quinine that's left inside the person's body. right? That's the variable of interest. It's the amount of the drug that's left inside the patient's body. We're interested in making future predictions of how much drug is still left inside the person's body. So more precisely, the variable of interest, if I have to erase something, let's erase this thing. The variable of interest is, okay, I also introduced notation in the process, AT, which is the amount in what units, the units they're using is in milligrams. The amount in milligrams of the drug that's left inside patient T hours after the initial dosage, initial dose. Right, that's the variable of interest. The amount in milligrams of the drug that's still left inside the person's body T hours after the dosage, T hours after the initial dose. Okay, this is the variable of interest. This is what we're interested in. We're interested in making future predictions of how much of the drug is still left inside the person's body. So the variable of interest is the amount in milligrams of the drug that's still left inside the person, T hours after that 50 milligram dose was given. Okay, and the first part of the question basically asks us to find a formula for AT. That's what the first part of the question asks. It asks us to find a formula for AT. Okay, so let's try to find a formula for AT. So what do we know about this function AT? Well, this question tells us that the drug leaves the person's body at a rate of 6% per hour. This interesting experimental fact that this drug leaves the person's body at a rate of 6% per hour. So then, that means that we know that this AT is changing by a certain percentage per unit time, right? It's leaving the person's body at a rate of 6% per hour. So it's changing by a certain percentage per unit time, 6% per hour. And we know from the theory, from the proposition that I just gave you, that if something changes by a certain percentage per unit time, it's an exponential function. Okay, we know from the theory that I gave you that if something changes by a certain percentage per unit time, it's an exponential function, and it's an exponential function of this form. AT equals to A naught times 1 plus r to the power of t, where A naught is the initial quantity, and r is the decimal representation of the percentage rate of change. Okay, right? That's what we know, because it changes by a certain percentage per unit time, it decreases by 6% per hour, the quinin leaves the person's body by 6% per hour, then that means that it's an exponential function. Okay, by that theory, if something changes by a certain percentage per unit time, it's an exponential function, and it's an exponential function of this form, where A naught is the initial quantity, and r is the decimal representation of that percentage rate of change, of the percentage change per unit time. And A naught is the initial quantity, and we know that initially the person got 50 milligrams of this stuff. So A naught is 50. And what's r? R is the decimal representation of the percentage rate of change. Well, the amount of quinin is leaving the body at 6% per hour. The quinin is leaving the body at the person's body at 6% per hour. So then the amount of quinin is decreasing. The amount of quinin inside the person's body is decreasing by 6% per hour. So it's minus 6% per hour. So then what's the decimal representation of that? The decimal representation is minus 0.06. So it's minus 0.06. Okay, can you see this? Because the quinin is leaving the person's body at 6% per hour, that means that the amount of quinin inside the person is decreasing by 6% per hour. So it's minus 6% per hour. So then the decimal representation of that is minus 0.06. So that's the decimal representation. So then this is, AT should be 50 times 1 minus 0.06 is 0.94t. And don't forget the units. This is a word problem, so don't forget the units. So it's 50 times 0.94t milligrams of quinin of the drug is left inside the patient T hours after the initial dosage. Okay? So left after T hours. The most important thing for the unit is to write milligrams. Okay, so then that's the answer. Okay, so this is the function AT, it's this exponential function. This many milligrams of the drug is still left inside the person after T hours. Okay, any questions? Any questions about this? Okay, let's do part B. Part B, which I erased, asks for how much of the drug is left inside the person after 24 hours. How much of the drug is left inside the person after a day and a night. So then, so they're asking for how much of the drug is still left inside the person after 24 hours. So you plug T equals to 24 into here. You plug T equals to 24 in here. So A 24 is 50 times 0.94 to the power of 24. And to calculate this, you need to use a calculator. Okay, to do this, you need to use a calculator. So if you use a calculator, you get around 11.33. And don't forget to write down the units, milligrams. So this many milligrams of the drug is still inside the person after 24 hours, after a night and a day. So after a night and a day, there's about 1/4 to 1/5 of the drug still left inside the person. And finally, the last part, we're asked to sketch the graph, of this function. Okay? We're asked to sketch the graph of this function. Note that the base A, A equals 0.94, but this is strictly less than 1. And when the base is strictly less than 1, that's the case of exponential decay. So this is the case of exponential decay. Okay, so this is the case of exponential decay. So then the graph should look like this. Okay, since it's exponential decay, the graph should look like this. So the horizontal axis is in the variable t for time in hours after the initial dosage. Okay, t in units of hours after the initial dosage. Okay, did I write that down clearly? Okay. And the vertical axis is in the variable a, which is the amount in mg, the amount in milligrams of the drug that's still left inside the person. So then, since it's exponential decay, the function looks like this. So meaning, initially at time t equals to 0, the function, the person had 50 milligrams of the drug inside of him or her, right? Initially, the person was given 50 milligrams, a 50 milligram dose of the drug. So they had 50 milligrams of the drug. And then the drug starts leaving the person's body through sweating and other means. And so the amount of drug inside the person's body starts going down, and decays to 0. Okay, so then this is the picture. Okay? And this is a pretty reasonable picture. This is a pretty reasonable picture. Okay. Now let's do another example. Let's do a second example. Let's do a second example. So the gross domestic product G of Switzerland, the gross domestic product G of Switzerland is $310 billion in the year 2000, in the year 2007, in 2007 AD. Again, let me check to see if everything's written clearly. Okay. And you're asked to give a formula for G in units of billions of dollars. Give a formula for G with units being billions of dollars, in billions of dollars. T years after 2007, T years after 2007 AD, if G increases by, and there are two possibilities. The first is 3% per year. And the second is $8 billion per year. Okay, so is everything clear? Is the whole board clear? Okay, so let me just read this again. The gross domestic product G of Switzerland is $310 billion in 2007 AD. And you're asked to give a formula, so this is a period over here, give a formula for this gross domestic product, G, in units of billions of dollars, T years after 2007 AD, if G increases by, and the two possibilities is that one, if it increases by 3% per year, and the second possibility is if it increases by $8 billion per year. Okay, so here's the answer. Okay, so again, for these types of problems, the first thing that I always do is I always first specify precisely the variable of interest. Okay, what time is it, by the way? Okay, for these types of problems, the first thing that I do is I always begin by specifying precisely the variable of interest. Okay, because again, by specifying precisely the variable of interest, it makes clear and precise what the problem is inside my head, even though specifying it may be redundant. And also, it makes clear a lot of other things too. For instance, it makes clear what the units are. Okay, so then what's the variable of interest? Clearly, the variable of interest is the gross domestic product of Switzerland, right? That's the variable of interest. We're interested in making future predictions of the gross domestic product of Switzerland. So the variable of interest precisely is GT, which is the gross domestic product. I'm going to write GDP. But now, what are the units? The question asks you to use units of billions of dollars. Not units of dollars, but units of billions of dollars. So the question asks you to use units of billions of dollars. So in billions of dollars, okay, the question asks you to use units of billions of dollars. Not units of dollars, but units of billions of dollars. Okay. Of Switzerland, T years after 2007 AD. I just write 2007. So that's the variable of interest. That's the precise variable of interest. You're interested in making future predictions of the GDP of Switzerland in units of billions of dollars, not units of dollars, but units of billions of dollars, T years after 2007 AD. And again, note that the units is in billions of dollars. So a standard mistake that people make is to use the wrong units, is to use the units of dollars instead of billions of dollars. Okay, the question asks you to use units of billions of dollars, and a standard mistake that people make is to use units of dollars instead of the one that the question asks. And then they lose points for that. They lose points for that. So this is a good example of why specifying the variable of interest at the beginning is useful, because it makes clear in your head a lot of things like what are the units you're supposed to use. It makes clear in your head what are the units you're supposed to use, as well as other items. Okay, so then now in the first part of the question, you're asked to assume that the GDP is growing by 3% per year. So you're asked to assume that the GDP, that GT is growing by 3% per year. So then, if it's growing by 3% per year, what is it growing by? It's growing by a certain percentage per unit time. Okay, if you're assuming that GT is increasing by 3% per year, then it's increasing by a certain percentage per unit time. And so, by the theory that we discussed earlier, by that proposition, since it's increasing by a certain percentage per unit time, it's exponential. It's an exponential function, and it's an exponential function which we can write in this form. GT equals to G naught times 1 plus r to the power of t, where G naught, what's G naught? What's G naught? G naught is the initial quantity. And remember, t equals to 0 is 2007 AD, right? Because it's t years after 2007. So then, and we knew, I erased it, but we knew that in 2007, the GDP of Switzerland was $310 billion. So G naught is 310, right? Because it was $310 billion, but then the units is in billions of dollars. So G naught is 310. And then what's R? R is the decimal representation of the percentage rate of change. It's the decimal representation of the percentage change per unit time. Well, in A, we're assuming that it's increasing by 3% per year. Since it's increasing by 3% per year, so it's plus 3% per year, then we know that R is the decimal representation of that, so it's 0.03. So it's 1 plus 0.03 t. So then GT is 310 times 1.03 to the power of t, and don't forget the units. The units is in billions of dollars. Billions, okay, let me just erase this. Billions of dollars. T years after 2007. Okay, so then that's the answer. Okay, any questions? Okay, so now let's do part B. In part B, we're asked to assume instead that the GDP is increasing by $8 billion per year. Okay, in part B, we're asked to assume instead that the GDP is increasing by $8 billion per year. So every year, the GDP increases by the same amount, which is $8 billion. Okay, every year, the GDP is increasing by the same amount, which is $8 billion per year. So what's this? This is the case of constant slope. It's the case of constant slope or constant rate of change. At every point in time, the slope is the same. At every point in time, the rate of change is the same. And the case of constant slope, what's the case of constant slope? It's the case of a straight line. It's the case of a straight line. It's a straight line with slope being $8 billion per year. So then, so this is a straight line, right? Because it's constant slope, which is $8 billion per year. At every point in time, the slope is $8 billion per year. So when you have a constant slope, that's a straight line. That's a straight line. So then GT is a straight line. And the initial amount of the straight line, which is t equals to 0, 2007 AD, is $310 billion. The units is in billions of dollars, so you write 310. And the slope is $8 billion per year. Again, units is in billions of dollars per year, so that is 8t. This many, and don't forget the units. The units is in billions of dollars. Billions of dollars, t years after. I just write $1 billion. $1 billion. 2 years after 2007. So then that's the answer. Okay. Okay. So now let me end this lecture with some miscellaneous problems involving exponential functions. Let's look at some miscellaneous problems involving exponential functions. So here are some miscellaneous problems involving exponential functions. So first, I'll remark. So recall that 2 points determine a unique straight line. So recall 2 points determine a unique straight line. Recall the fact that 2 points determine a unique straight line. So if you so that was property one for straight lines that we discussed. 2 points determine a unique straight line. So you have 2 distinct points. Then there's one and only one straight line crossing those 2 distinct points, namely this straight line. Okay, so recall this principle 1 for straight lines. 2 points determine unique straight line. Okay, 2 points determine unique straight line. And this is actually a very nice property of straight lines. Most functions don't have this property. Most functions don't have this property. For instance, 2 points don't determine a quadratic. 2 points don't determine a degree 2 polynomial. 2 points don't determine a cubic. 2 points don't determine a degree 3 polynomial. 2 points don't determine, say, a sine function. 2 points don't determine a cosine function either. So most functions don't have this property. This is a very nice property. Straight lines are so nice that 2 points determine a unique straight line, and most functions don't have this property. Most functions don't have this property. However, it turns out that exponential functions are so nice that 2 points also determine an exponential function. So in fact, two points also determine a unique exponential function. Okay, this is a really nice property of exponential functions. This is a nice property that straight lines have, and it's a nice property that exponential functions also have. Most functions don't have this property. Sine functions don't have this property. Cosine functions don't have this property. Higher degree polynomials don't have this property. Most functions don't have this property. It's a nice property that's very rare. So straight lines have this property. 2 points determine unique straight line. And also exponential functions, which is the second class of most important functions in this class. The second class of most important functions in this course also have this property. 2 points determine unique exponential function. Okay, let's look at an example. Example. Say that PT is an exponential function such that P1 is equal to 3, P5 is equal to 6. Find this exponential function. Find PT. Okay, so what do we have? We have this unknown function, and we're told, okay, this function is an exponential function. It's an exponential function. Okay, so we have this function, which we don't know what it is. We don't know what it is yet. And we're told, okay, it's an exponential function. And we're given 2 points on this exponential function. We're given 2 points in this exponential function. We're given the point 1, 3, and we're given the point 5, 6. But now remember what I just said. Remember what I just said and erased. 2 points determine a unique exponential function. 2 points determine a unique exponential function. So there is one and only one exponential function. Exponential functions are so nice that like straight lines, that 2 points determine a unique exponential function. Exponential functions are so nice that like straight lines, 2 points determine a unique exponential function. Most other functions don't have this property. So there's a unique exponential function. There's one and only one exponential function that's passing through these 2 points. Okay, there's one and only one exponential function that passes through these 2 points. And so we're asked to find out what that exponential function is. Okay, we're asked to find out what this exponential function is. Okay, so what do I do? How do we find out what this exponential function is? What I would first do is I would write down the general definition of an exponential function, the general form of an exponential function. So here's the general form of an exponential function. Here's the definition of an exponential function. So that's the first thing I would do. Okay, write down the definition of an exponential function. So then to determine what the precise exponential function is, what we want to do is we want to solve for P naught, the initial quantity, and we want to solve for A. Okay, once we have the initial quantity P naught, and once we have the base A, then that completely determines the exponential function. So then how do I solve for P naught and A? Well, what I do is I just plug these 2 points into this function, and then just do a lot of algebra. Plug these 2 points into this function and do algebra. So first, plug 1P into this function. So we get 3 is equal to P, plug in T equals to 1. 3 is equal to P1. And so you plug in T equals to 1 to here, so that's P naught times A to the power of 1. Okay. Now plug in 5, 6. Plug in 5, 6. So 6 is P5. So plug T equals to 5 in here, so that's P naught times A to the power of 5. Okay, so then let's gather those 2 things together. Just let's clean it up by gathering them together. So I have P naught A 1 is equal to 3. Okay, I just gathered this over here and gathered this over here. And P naught A to the power of 5 is equal to 6. So now the next thing I'll do is I'll divide the bottom by the top. I'll divide the bottom by the top. So I divide 6 by 3. If I divide 6 by 3, well, 6 is equal to this, and 3 is equal to this. So if I divide 6 by 3, it's like dividing this by this. So I divide P naught times A to the 5th over P naught times A to the 1. And what do we have? We have, first of all, that these P naughts cancel out. So then I'll be dividing A to the 5th by A to the 1. So I'll be dividing A to the 5th by A to the 1. And so what I'll be doing is I'll be dividing 2 exponentials with the same base. And remember, if you divide 2 exponentials with the same base, there's a rule which says that if you divide 2 exponentials with the same base, so these are 2 exponentials with base A, you divide 2 exponentials with the same base, it's the same as subtracting the powers. It's the same as subtracting the powers. So it's 5 minus 1. 5 minus 1 is 4. So it's A to the 4th. So then bring this down. A to the 4th is equal to 6 divided by 3, which is 2. Okay, next. Okay, so far so good. Any questions? Any questions? Next, let's isolate the A. To isolate the A, I take both sides to the 1/4 power. So if I take the right-hand side to the 1/4 power, I have to take the left-hand side by the 1/4 power. And then, remember, over here we have repeated exponentiation, right? We're taking A to the 4th, and then we're taking the whole thing to the power of 1/4. Well, repeated exponentiation is the same as multiplying the powers together. That's rule. Okay, let me just write down the rule for here, first of all. Over here, I used rule, the rule which says that if you divide 2 exponents with the same base, it's the same as subtracting the powers. That's rule 5. And over here, I'll use the fact that if you repeat exponentiation is the same as multiplying the powers together to get a to the 1, or a, and that's rule 2. Okay, so then I have a is equal to 2 1/4. So a is equal to 2 to the power of 1/4. And if you want, you can write that into pt. So pt is equal to p naught times 2 to the power of 1/4 to the power of t. And then what remains to completely determine the exponential, what remains is to determine p naught, to determine b naught, p naught. And what we can do is we can just plug in one of the 2 points to completely determine p naught. So we had that 3 is p1, so that's p naught times 2 to the power of 1/4 to the power of 1, which is itself. So p naught is equal to 3 divided by 2 to the power of 1/4. So then we have pt. pt is 3 divided by 2 1/4 times 2 to the power of, if you want, t over 2. Okay, so that's the answer. You can write it like this. You can write it like this if you want. You can simplify a little bit by writing like this. And you can write it in various other ways too. Okay, so then that's the answer. Okay, that's the answer. And if you want, you can, if you're more comfortable, you can put everything in decimal form too. So that's the answer, by the way. That's the answer, by the way. But if you want, if it's more comfortable for you, you can use a calculator and put everything in decimal form. You can use a calculator and put everything in decimal form. Okay, if it's more comfortable for you. So for instance, a second way, if it's more comfortable for you, is to just use a calculator. Use a calculator. Use calculator. And put everything in decimal form, if that's more comfortable for you. So remember, a was 2 1/4. If you use a calculator, I'll just write, if you use a calculator, then that's approximately 1.19. Okay. If it's more comfortable for you, you can use a calculator and put everything in decimal form. So then pt is equal to p naught times 1.19 to the power of t. And then to solve for p naught, you use one of the points. Let's say we use p1 is equal to 3. 3 is p1, so that's p naught times 1.19. So then p naught is 3 divided by 1.19, and that's approximately 2.52. So then the function becomes pt equals to 2.52 times 1.19 to the t to the power of t. Okay, so if you want, you can use a calculator and put it all in decimal form. Okay, and there's other equivalent ways too, which are equally legitimate, which are okay. Okay, let's do one final example. Let's do one final example. Okay, what time is it? Okay, let's do one more example. E.g., say that pt, which is this exponential function, say that this exponential function is the population of a village t years after a certain time, t years after 30 BC, is the population of a village t years after 30 BC. Okay, so say that this exponential function is the population of some village t years after some time which we say is t equals to 0, namely 30 BC. 30 BC is t equals to 0. Then the question asks, by what percentage per year does the village grow or shrink? By what percentage per year does the village grow or shrink? Okay, so you're given this exponential function, and that's the population of a village t years after 30 BC. 30 BC is designated as t equals 0. And you're asked by what percentage per unit time does the village grow or shrink? By what percentage per year does the village grow or shrink? Okay, so here's the answer. So recall the proposition that I gave you, the word problem theory, the word problem proposition that I gave you, that theory that I gave you at the beginning, which says that if you have pt equals to p naught times a to the t, then a, okay, this is from the proposition, the abstract proposition that I gave you at the beginning, then a has the form 1 plus r. If you have an exponential like this, then the base can always decompose as 1 plus r, where r is the decimal representation of the percentage rate of change. Decimal representation of the percentage change per unit time, of the percentage rate of change. Okay, whenever you have an exponential like this, then the base a can always be decomposed as 1 plus r, where r is the decimal representation of the percentage change per unit time. This is always true. This is always true for any exponential. This may or may not be useful. This may or may not be useful, but this is always true. So then, over here, what's the base? The base is 1.07, so this is the base a. Okay, this is the base. The base a is 1.07, so that's 1 plus 0.07, so then this is r. This is r. So this is a and this is r. And remember what r is. R is the decimal representation of the percentage rate of change. So then, since this is the decimal form of that percentage, we know that the population of the village is growing by 7% per year. So it's growing, and it's growing by 7% per year. Population of village is growing. It's growing. It's not shrinking, it's growing, right? Because this is plus 0.07. So it's growing by 7% per year. Okay, so that's the answer. Okay, the population of the village is growing by 7% per year. Okay, so what time is it? Okay, so it's 1 hour and 8 minutes. Okay, so just under. So I finished in time. Okay, so I'm finished for today. Okay, so